Hello there, Mr. Wilson here again for what is part 3 of these revision lessons on matrices for GCSE Further Maths. Now, if you haven't already, I would suggest subscribing, and because that means you'll never miss any videos, because there's an upload every single day, ranging from GCSE Normal Maths, GCSE Further Maths, and A-Level Maths. So there is something for hopefully most people who are wherever they are in their journey of studying maths. So let's jump into this part 3, which is all about matrix transformations. Now, this tends to be one of the most difficult parts about matrices, and actually this was a suggestion by a few commenters. So if you have a topic that you would like me to cover, then please let me know in the comments below. I say it often, but I don't think people use that sort of tool enough, so please use the comments and let me know what you would like, because somebody did request this topic, and it is something that I was going to do anyway, because it is quite a difficult idea. So just before we get into matrix transformations then, and we're going to try and cover most of the matrix transformations, let's just recap on how we multiply a matrix with a vector. Now technically, and we'll see this in a second, technically this is actually representing a coordinate in this case. So we've got a matrix and we've got a coordinate. So remember, this is a 2 by 2 matrix and this is a 2 by 1 matrix, and as we talked about in the previous part, because these numbers are the same, these dimensions are the same, we can multiply these and our answer is going to be a 2 by 1 matrix, which again is just another coordinate really. So 2 times 3 is 6, plus 5 times negative 1, which is negative 5, so that's going to give us 1. And then 1 times 3 is 3, plus 3 times negative 1 is negative 3, so that's going to give us 0. So what this is actually showing is that when you multiply this matrix by what is technically a vector, but is actually representing a coordinate in this example, because we're talking about transformations, it equals this coordinate. So in other words, when you multiply this matrix by this coordinate, it's moved to this coordinate. So there's been a transformation that's happened here. And that is the basic idea behind matrix transformations, is that a matrix transformation, matrices are just used to describe a transformation. And transformation is just a rule that moves a coordinate, well, every coordinate, to a different coordinate. So in our previous example, this matrix moves this coordinate to this coordinate, and if we had a different coordinate, it would perform the same rule, this 2, 5, 1, 3, and move it to another coordinate. So let's sort of see this in a little bit of action then. Transform each coordinate by the matrix 3, 3, 1 to negative 1. So let me just scroll down a little bit so we can fit that in. So we've got the coordinate here 2, 1 for B, and we've got negative 1, negative 2 for A. So if we want to transform a coordinate by a matrix, right, then you write the matrix first, so 3, 1, 2, negative 1. And let's go with coordinate A first, which is negative 1, negative 2. So you always write it x, y. So you write the matrix A, B, C, D, whatever that is, and then you write x, y, the coordinate, with the numbers on top of each other like that. Then you just perform your matrix multiplication, because this is a 2 by 2, this is a 2 by 1, so you're going to get another coordinate out the other side. 3 times negative 1 is negative 3, plus 1 times negative 2 is negative 2, so that's going to be negative 5 altogether. And then 2 times negative 1 is negative 2, negative 1 times negative 2 is positive 2, so that's going to give you 0. So this coordinate A moves to negative 5, 0. So we're going to call this A with a little dash. The little dash, or the apostrophe, represents the idea that this is the transformed point of A. So that coordinate A is going to move over to negative 5, 0. And we could do the same thing for B. So we could do 3, 1, 2, negative 1, and the coordinate B is 2, 1. So we get 3 times 2 is 6, plus 1 times 1 is 7. Now if you want to recap on how I'm doing this, I multiply every value in the row of the left matrix with every value in the column of the right one. So 3 times 2 plus, moving across, 1 times 1, moving down on the other one, which is 7. And then 2 times 2 is 4, plus 1 times -1 is -1, so 4 plus -1 is 3. So this coordinate B is going to move to 7, 3, which is going to be somewhere here, and that's going to be B dash, right, 7, 3. So, yeah, some kind of strange stuff that's happening here, because A goes over to the left over here, but B goes all the way over to the right over here. But that is just what the rule is telling us to do. Now, we technically don't need a coordinate grid, right? So if they give you a question like this, work out the image of the point 1, 3 for the transformation defined by the matrix 3, 6, 1, 0. Well, an image is just where something ends up after a transformation. So all you need to do is take your matrix and again multiply it by the point that you're given, 1, 3, and you're going to get 3 times 1 is 3, plus 6 times 3, well that's going to be 18. 3 plus 18 is 21. 1 times 1 is 1, plus 0 times 3, which is 1. So that means the image of the point, 1, 3, is the coordinate 21, 1. Right? So 1, 3 is going to move over to 21, 1. That's just the rule. It looks really weird and awkward, but that is genuinely how this works. And we can even do it for a whole shape. Let me just move this. Ooh. I have totally moved the wrong thing there. Let me move my matrix down just so I can scroll down a little bit so you can see the whole triangle here. So I want to transform this whole triangle by the matrix 2, 0, 0, 2. Okay, so you'll notice it looks very similar to the identity matrix. Remember, the identity matrix is the matrix 1, 0, 0, 1. And this one is the matrix 2, 0, 0, 2. So just an interesting point, but you know, nothing to really well, it is slightly interesting, we'll find out in a second, but nothing to really worry about right now. So we just need to take each of these coordinates and multiply by the matrix, and then it asks for A dash B dash C dash. Let's call this one A, this one B, and this one C. So A is the coordinate 1, 0, so we do 2, 0, 0, 2 times 1, 0. Okay, we're going to work that out. I need to scroll a little bit down. No, we're all good. So I do 2 times 1 is 2, plus 0 times 0 is 0, and then 0 times 1 is 0, plus 2 times 0 is also 0. So 1, 0, which is A, is going to move to 2, 0. That's A dash. So this is going to be the coordinate 2, 0. Well, the coordinate B, that's the coordinate 1, 3. So I just need to do my matrix times the coordinate 1, 3. So I get 2 times 1 is 2, plus 0 times 3, which is still 2. 0 times 1 is 0, plus 2 times 3, which is 6. So the coordinate 1, 3 is going to go to 2, 6. So it's going to go all the way up here. That's B dash. So this is the coordinate 2, 6. And then C is the coordinate 3, 2. So I just need to do the same thing, but for the coordinate 3, 2 instead. So I do 2, 0, 0, 2 for the coordinate 3, 2. And this gives me 2 times 3, which is 6, plus 0 times 2, which is 0. So this is 6. 0 times 3, which is 0, 2 times 2 is 4. So that this is going to go to the coordinate 6, 4, which is here. So this is C dash, the coordinate 6, 4. Now you might actually notice, maybe you have, maybe you haven't noticed, that the coordinates of A dash, B dash, and C dash, the image, is 2 times the original coordinate, right? And that's very special, that's very unique. We're going to talk about why that is in a second, well, a little bit later, but for now, we just need to be satisfied with the idea that that is how we do a transformation. We just multiply a matrix by a coordinate and we get the image. And in this case, not coincidence, in this case, every coordinate is 2 times bigger than the original. So we have a shape that is 2 times bigger than its original shape. Okay, let's move on then. So one thing that you can use when talking about transformations is something called a unit square. right? And I'll explain more about this and why it's really helpful in a second. But we're going to look at a lot of transformations, and the unit square is really useful. So the unit square is a square that has area of 1. It has coordinates 0, 0, 1, 0, 1, 1, 0, 1. So you get a square on a grid. So let me show you. So this is the unit square. So we've got A, B, C, D, and I've coloured in. I don't know if you can sort of see it in the clarity, but I have coloured these dots. So this one's like a red, orange colour. This one's green, purple, and blue. So these are different colours, and those colours are going to help us understand different transformations in a second. So what I'm going to do is I'm going to take this square, and I'm going to perform a transformation on it. I'm going to basically, I know what coordinates I started with, and I hopefully know what coordinates I'm going to finish with, and I'm going to sort of compare what has actually happened to the coordinates. So let me show you. So an example then, let's say I take my unit square, so there's my unit square, looking wonderful, and I reflect it in the y-axis. Right, so I'm going to do a reflection in the y-axis. What's going to happen to that unit square? Well, this red point here, well, that's not going to move because it's on the line of symmetry, right? So that's going to stay where it is. So this is going to be the coordinate of D dashed in this case because I've called this D. And same goes for C, right? That coordinate's not going to move either because it's also on the line of symmetry. B, on the other hand, well, that's going to be reflected over here. That's going to be B dash. And A is going to be over here, isn't it? That's going to be the image of A. So in other words, the C coordinates haven't changed, but now B has gone from being, well, A has gone from being 1, 0 to now being minus 1, 0. And B has gone from being 1, 1 to being minus 1, 1. Right? But the other coordinates haven't changed. So this is what you end up getting. Right? So here this coordinate hasn't changed, but B has obviously changed from being 1, 0 to minus 1, 0. Now, have I got it on the next? I'm just checking my slides. No, that's the x-axis. So here, what has happened then is, if I flick back to the first one I had, so these coordinates have changed, but you'll notice the y-coordinate never changes in these transformations. The y-coordinate does not change, right? It goes from being 1 to being 1, right? Because the reflection of the y-axis does not change the y-coordinate. But what has changed is the x-coordinate has gone from being positive to now being negative. And it's gone from being positive to now being negative. The reason why it doesn't affect C and D is because the x-coordinate of C and D is 0. And so therefore the negative version of that would also be 0. So basically, there's a matrix that I don't know. But what I do know is that when you transform a coordinate, right, as we've just done with our unit square, you've now got a coordinate where the y-coordinate has stayed the same, so it was y in this one and it's y in this one, but the x-coordinate has turned negative, so it's gone to minus x. So basically you've took a matrix, and a reflection of the y-axis is where all the y-coordinates stay the same, but the x-coordinates turn negative. Now there is a matrix that describes this rule, right? There has to be, because there's a matrix that describes pretty much all of these transformations. So the y-coordinate stays the same, right? That must mean there must be a 1 in this bottom right hand box, because when you do your matrix multiplication to get this number here, you do this number times this number plus this one times this one. So in order for there to be a y here, there's got to be a 1 here, and therefore there's got to be a 0 here, because you don't want any x's here, you just want a y. So it's got to be 0, 1 on the bottom. But the x-coordinate is turned from positive to negative, so how are you going to do that? Well, there's got to be a minus 1 in this first box and a 0 here, because minus 1 times x is minus x, plus 0 times y is still minus x. So that's where you get this minus x from. So I've kind of done the unit square and then thought logically working backwards to try and work out what the matrix is. And if you have a look, or I did it earlier, that is the matrix for a reflection in the y-axis. it is minus 1, 0, 0, 1. That is a reflection of the y-axis. So if you have any shape whatsoever and you perform that matrix on it, it would be an exact reflection in the y-axis, because all the x-coordinates would turn negative, but the y-coordinates would stay the same. So that's what it is. Now, if you are curious, by the way, I would personally get a stack of revision cards like these, and I would sort of write these down, because I think a lot of students like to remember them. Although, as I've just shown you there, even if you couldn't remember them, you could still use your unit square method and work through logically to work these out. But a lot of students like to just sort of remember what they are. Minus 1, 0, 0, 1 is a reflection in the y-axis. Okay, let's try the same process again then, but this time I want to do a reflection in the x-axis. So I've got my unit square again. And if I want to do a reflection in the x-axis, well, this point here is going to stay where it is, and A is going to stay where it is because it's on the x-axis, and I want to do a reflection in the x-axis. This B here is going to go here, so it goes from being 1, 1 to now it being 1, minus 1, right? Because it's on 1 across, 1 down. And C goes from being 0, 1 to now being 0, minus 1. So in other words, right, what has happened here then? Well, all the x-coordinates have stayed the same, right, because it goes from being 0 to being 0, and from being 1 to being 1. So you've taken a coordinate, and the x-coordinates have stayed the same. They have not changed. But the y-coordinates have gone from being 1 to being minus 1, and same on this side. So the y-coordinates have now turned negative. It's the same number, same value, so it's still y, it's just negative y, it's just the negative version. So I know there must be a matrix that when I multiply it by my coordinate, I get x minus y, which is a reflection in the x-axis. Well, this must mean there must be a 1, 0 on the top, because the only way to get x is if I do 1 times x and plus 0 times y, to just leave x. So it must be 1, 0 on the top, but then it must be 0 minus 1 on the bottom row, because 0 times x is 0, plus minus 1 times y is negative y, so that's going to give me the negative y on the bottom. So you can check by doing a matrix multiplication like we did earlier to check to see, is this matrix times xy going to give you the transformation that you are wanting? And if I reveal this, it should reveal, there you go, see? 1, 0, 0, minus 1 is a reflection in the x-axis. Now you might notice immediately that a reflection in the y-axis and the x-axis are very similar, right? If we flip back, the y-axis was minus 1, 0, 0, 1, and in the x-axis it's 1, 0, 0, minus 1. So these two values have basically swapped over. And you'll see there that I did it earlier. What about then a reflection in the line y equals x? Okay, well, if I draw the line y equals x in with my line tool, so y equals x is this line here. What happens when I reflect the coordinates in this? And again, we can use the same method. Well, B and D are going to stay where they are, aren't they? We basically, there's a posh word for this, it's invariant. If a point stays where it is after a transformation, it is invariant. And then this coordinate here, C, well, that's going to be reflected over the other side. That's actually going to land on A, right, which is a bit weird. So C goes from being 0, 1 to now being 1, 0. And similarly, A actually lands where C is going to be. It lands on the other side. So A goes from being 1, 0 to being 0, 1. So, in other words, right, what's actually happened here then? So you've taken some coordinate, x, y, and what's happened? What has happened to these coordinates? Well, they've gone from being 0, 1 to being 1, 0, and A's gone from being 1, 0 to 0, 1. Now you might say, oh, well, I've taken away 1 and then added, and I've added 1 and then taken away 1. That's not really what's happening here. What's happened is, and some of you might see it, is the y coordinates have swapped over, right? because it's gone from being 0, 1 to being 1, 0. And actually, if you pick any coordinate, so this coordinate up here, 2, 4, the reflection is 4, 2, right? So the x and y coordinates have swapped over. So it's turned into this, yx. So it's the same values, but the other way around. Okay, what matrix is going to give me this transformation then, where the x and y coordinates swap over? Well, there has to be a 0 to begin with, because I don't want x on the first value. So 0 times x is 0, but then 1 times y is y. So y is going to appear in that first box. And then here it's got to be 1, 0, because 1 times x is x, plus 0 times y is 0. So that just leaves me with x. So I just did a little quick check there, multiplied the matrix by the coordinate, and it swaps over the x and y values. Now you might notice straight away that 0, 1, 1, 0 looks a lot alike to the identity matrix, which is 1, 0, 0, 1. Please do not get these confused, right? The identity matrix is a very special matrix in that when you multiply it by any vector or any matrix, you get the same matrix, the original one. Whereas this 0, 1, 1, 0, which if I reveal, there we go, that is a reflection in the line y equals x. So again, reflection in the line y equals x. I'll have a little summary sheet at the end, so please don't think that you have to sort of write them down as we're going through. I have a slide all at the end where it has all the transformations on. Now you could do, so that was the matrix for y equals x. You could do the exact same method for y equals minus x. And if you do that, you actually find it's the same matrix, but just with negative values here. So you could do the exact same process for the line y equals minus x. And again, I drew my dots in different colours of where I've translated it. But you get 0, minus 1, minus 1, 0, like that. And so you get that matrix there. Okay, what about a rotation at 180 degrees about the centre then? Well, a rotation 180 degrees about the centre, well, D is the centre, so the centre of rotation, so that's going to stay where it is. It's invariant. This coordinate is going to appear on the other side, isn't it? Because if you rotate something 180 degrees, it's on the other side. So this point here, which is 0, 1, is now going to be this coordinate here, which is 0, minus 1. And this coordinate here, which is 1, 0, is now going to be over here, which is minus 1, 0. And this purple one here, which is 1, 1, is now going to be over here, which is minus 1, minus 1. So in other words, all the x coordinates have turned negative and all the y coordinates have turned negative, because in this blue point here, point A, the x coordinate's gone negative, but you can't really see what's happened to the y coordinate. So you've taken a coordinate and the x coordinates have gone negative, right? But it's the same value, just negative. The y coordinate has also gone negative, because here you can clearly see with the green one, C, it's gone from 1 to minus 1. So the y coordinates have turned negative. So what matrix is going to give me the same as changing all the x coordinates to negative and all the y coordinates to negative? Well, it must be minus 1, 0, 0, minus 1. Because minus 1 times x is minus x, 0 times y is 0, so that's going to be minus x. 0 times x is 0, plus minus 1 times y is minus y. So that's going to give me minus xy, and if I do a little reveal, there we go, minus 1, 0, 0, minus 1. This is not to be confused with the reflection in the line y equals minus x, even though, right, they give very similar shapes. You can clearly see here that green point there translates to here in the reflection y equals minus x, but in the rotation the green point goes from here to here, so it's not exactly the same. It gives the same shape, but it's not technically in the same position because the points are in different places. And you'll notice this with other shapes, so just be really careful between this matrix and this one, because they look very similar but are in different, the numbers are in different positions, the elements are in different positions, so that's why you get this. What about a rotation 90 degrees clockwise then? See, we're going through all of them right now. So If you take these coordinates again, you rotate 90 degrees clockwise about the centre. Well, D again is invariant. A is going to be rotated round to here. If it's 90 degrees clockwise, it goes that way round. So it goes from being 1, 0 to now being 0, minus 1. This B point over here, right, it's going to be rotated around to here. So this B point, which is 1, 1, is now going to be here, which is the coordinate 1, minus 1. Okay, interesting. Then this C point here is the coordinate 0, 1. When you rotate it 90, it actually lands on A, so it's going to be 1, 0. Okay, so what's actually happened to the coordinates then? Let's have a little analysis on all of these. Well, this one has gone from being 1, 0 to being 0, minus 1. So it's like you've flipped them over, but then you've turned x negative, which is a bit weird, right? Or you've turned what now is the y coordinate, but what was the x coordinate? Negative. So you change the x coordinate to be negative, and then you swap them. Let's see if that sort of idea works for the rest of them. So for this one, 1, 1, well, it goes from being 1, 1 to now being 1, minus 1. So you've swapped them over and then turned what was the x-coordinate negative. It's now in the y-coordinate position. And this one still matches, right? You swap them over, so it becomes 1, 0, and then you turn the y-coordinate, which was the x-coordinate, negative. So it's still 1, 0. So that holds true, right? You take a coordinate, and the transformation 90 degrees clockwise is you swap them over, right? So it now becomes yx. But what is now the y-coordinate, which used to be the x-coordinate, is now negative, right? So that's what's happened here. To go from 1, 0 to 0, minus 1, you've flipped the x and y coordinate, and then you've changed what is now the y-coordinate, but what was the x-coordinate, negative. So you get this. So what matrix is going to give us this transformation then? Well, it's got to start 0, 1, because you want y at the top, right? So it's got to start 0, 1, because 0 times x is 0, 1 times y is y. So it's got to be 0, 1. Then on the bottom row, it's got to be minus 1, 0, because minus 1 times x is minus x, 0 times y is 0. So I flip them over, I've changed the x-coordinate negative, and I believe in an amazing, here's what I did earlier, Blue Peter moment, 0, 1, minus 1, 0. So that is a rotation 90 degrees clockwise about the centre. What about a rotation 90 degrees anti-clockwise then? So anti-clockwise, right, you rotate the other way to what we just did. And remember, if it was 270 degrees clockwise, that would be the same as 90 degrees anti-clockwise. Obviously not doing both because they're the same transformation. So this coordinate's going to go here. So it goes from being 0, 1 to now being minus 1, 0. This B coordinate goes from being 1, 1 over here to now being minus 1, 1. And the A coordinate actually lands on C. So A goes to C. This is the coordinate 1, 0, and it goes to being 0, 1. So what's happened here then? Well, it's actually the complete opposite of the previous one. In the previous one, the x and y coordinates changed, and what is now the y coordinate but used to the x coordinate is now negative. In this one, we've still swapped them over, right? Because if you look at the green one, we've swapped them over, but now what is now the x coordinate but used to be the y coordinate is now negative, right? So you've taken a coordinate, x, y, you've swapped them over, so it's now yx, but now what is now the x coordinate but used to be the y coordinate is now negative. That's how you go from 0, 1 to minus 1, 0. You've swapped them, but then changed the first coordinate to be negative. So what matrix is going to give me this transformation? Well, it's got to start 0, minus 1. That's the only way you're going to get minus y here, because 0 times x is 0, minus 1 times y is minus y. And then this bottom row's got to be 1, 0, because 1 times x is x, plus 0 times y, which is 0, so it's still x. So in another, here's what I did earlier, 0, minus 1, 1, 0 is the transformation there. So I think there's maybe one more. So this one here. right? Enlarge by scale factor 2, centre 0. So scale factor 2 means everything gets 2 times bigger from the centre of enlargement. Well, obviously, D is still invariant because it's on the centre of enlargement. A goes from being 1, 0 to now being 2, 0 because it gets 2 times further away. So it ends up here. C goes from being 0, 1 to being 0, 2. And B goes from being 1, 1 to now being 2, 2. Which is kind of easy. So basically all the coordinates have just got 2 times bigger, right? So it's gone from being... So you've taken the coordinate, whatever the coordinate that might be, and you just multiply both the x and the y by 2. Obviously in this one it looks like the y coordinate is just being multiplied by 2. But obviously it's easier to see with 1, 1 that both the x and the y are being multiplied by 2. So it goes from xy, the coordinate, to now being 2x, 2y. Well, how are we going to get this? What matrix is going to give us this transformation? Well, it's got to be 2 here, because 2 times x is 2x. But then you want a 0 there, because 0 times y is 0, because you don't want anything else in this top box. And then it's got to be 0, 2, which 0 times x is 0, 2 times y is 2y. Now, here's one thing I want to point out then. You might notice that this looks really similar to the identity matrix, which is 1, 0, 0, 1, right? With 1s down the leading diagonal. It's 2, 0, 0, 2. In actual fact, this is the whole vibe of an enlargement. So when you have an enlargement by whatever scale factor, as long as it's centered 0, then whatever scale factor you want to enlarge by, it's just the scale factor times the identity matrix. So for example, if I wanted to enlarge by scale factor 5, then it would be the matrix 5, 0, 0, 5. Right? It's just 5 times the identity matrix 1, 0, 0, 1. Because the 1, 0, 0, 1 is the matrix that does nothing, it just keeps it the same size. So 2, 0, 0, 2 keeps it in the same position, but now it's 2 times bigger from its original size. But the original centre point is in the original position. So if you want to enlarge by any scale factor, you could even do scale factor 1/2. It would be 0.500, 0.5, right? If you wanted to do a half scale factor. So the key idea here is that if you want to enlarge by a point by a scale factor, then it is just the scale factor times the identity matrix in whatever circumstance, whatever scale factor you want. And you get this, and as we've already discussed, it's 2, 0, 0, 2. So as promised then, let me show you my little cheat sheet to finish off then. So just to recap everything that we've done, and this, if you could sort of move my head out of the way a little bit, let me scroll down a little bit, and then I can squeeze everything without having to move my head. So this almost cheat sheet, I would definitely be getting on some revision cards. So I'd write the matrix, or I'd write the transformation on the front, and then the matrix on the back. And then you can either do it where you look at the transformation and then try and work out the matrix. That is more difficult. Or you give the matrix and then you have to work out the transformation. Either is quite tricky. Personally, I think when they tell you a transformation, working out the matrix is more difficult. But it's whatever you want to do. But I would definitely get some revision cards and write these down, because the more you repeat the matrices to yourselves, the more likely you are to remember them. And yeah, you can work them out, but do you want to be spending loads of time in the exam trying to work out a matrix that you, even if you can't remember, just having some idea of what it might look like, just to save you a little bit of time? It's not the be all and end all, and personally I would work them out just to double check, because I know for me personally I sometimes misremember things, like key facts. But I think students that tend to remember them tend to sort of have a better idea in general about matrices, and they can sort of work it out from there, even if they don't fully remember it. But again, students can misremember in the exam, so make sure you obviously double check. But these are the matrices that we covered. Obviously the identity matrix, absolutely key. it is the matrix that basically does nothing, right? It doesn't do anything. It just, the shape goes to the same shape. Enlargement by scale factor k about the origin is just k0, 0k, where k is the scale factor. Because remember, as we discussed, it's just k times the identity matrix. So it's the same sort of pattern with the leading diagonal, but by scale factor k. A reflection in the x-axis, or the line y equals 0, is 1, 0, 0, minus 1. A rotation 90 degrees clockwise is 0, 1, minus 1, 0. A reflection in the y-axis, minus 1, 0, 0, 1. A rotation 90 degrees anti-clockwise is 0, minus 1, 1, 0. A reflection in the line y equals x, 0, 1, 1, 0. And a rotation 180 degrees about the origin, minus 1, 0, 0, minus 1. And a reflection in the line y equals minus x, 0, minus 1, minus 1, 0. So, like these four have been highlighted here, these are sort of the key four, where if you remember those, you can sort of remember the other four because they're linked to them. However, I would just give them all a good go, and like I said already, the main thing that I've seen students do is get them on revision cards and try and remember them all. Okay then, I would personally, I'll pause the screen and then you can jot down whatever you need, but I am going to leave it there for this part. In the next part, which should be the last part, we're going to look at some exam style questions. We're going to look at when you do multiple transformations after each other, kind of what things happen. We're going to look at how do you go and answer an exam question when it says, oh, you do this transformation followed by this transformation followed by this transformation. What matrix describes all three of those? Stuff like that is what we're going to look at. I'm going to look at, how do we go about remembering these and recalling them for those exam questions. So all them things we're going to cover in the next one. But like I said, this cheat sheet here is crucial for remembering matrix transformations. And also, not only getting them on flashcards is really helpful, but also just using them. So when we go through some exam questions in the next part, I want you to sort of be doing the same sort of idea. Just get loads of exam questions on matrix transformations. And I mean, you can even start with this sheet in front of you, just to help you out as you sort of begin it, and then slowly remove the help as you sort of become more comfortable with remembering them. But we'll talk all about those tips in the next part. But hopefully you've enjoyed this video. This has been probably one of my longest videos actually, but I think it was well worthwhile going into a lot of detail. I think there was a lot of repetition in the method, but I think some people needed that just to offer that bit of repetition and clarity in where I'm getting these answers from. They don't just sort of come out of thin air. It's very much a sort of logical process, but it is the same process every time to try and work out what the matrices are for different transformations. But as with any video, but especially this video because it is quite a difficult topic, if there are any questions, please let me know in the comments below. I do try and check up on the comments pretty much every day and answer to those comments as and when I can, but I do try and respond to everybody who asks a question. When I see that comment and I have the time to respond to them. But yeah, please let me know if you have any concerns about this topic at all. All I want to say though is I hope you have thank you so much for watching, and I hope you have a fantastic day.